Okay, so to continue from last time, we're going to be looking at some more conditional probability problems, this time focusing on the idea of independence. So independence means that the probability of A happening, given that B has already happened, is the same thing as the probability of A happening. So not all probabilities are completely separated. A lot of times, when one event happens, it changes the likelihood of another event happening. For example, looking at this comic here, this is what are the odds of two ropes breaking at the same time? Well, he seems astonished by this, but it's because he's assuming that those two things are independent. When one rope breaks, it puts a lot of extra strain on the other ropes. So once one rope breaks, another one is more likely to break as well. So when we think about independence, we always want to ask ourselves when we're starting a probability problem if two events are independent or not. So let's say we shuffle a deck of cards, turn over the top card and take a look at it, put it back in the deck and shuffle, then take off another card. So if we define events as that first card is a heart and the second card is a heart, these two events would be independent. Because we took that first card, put it back in the deck and reshuffled, it doesn't change the probability of the second event, right? We had a 1 out of 4 chance in event A, we have a 1 out of 4 chance in event B, and it doesn't matter what happened in A, event B will always have the probability of 1 out of 4. However, if we did something kind of like this, except we didn't put the card back, so shuffle a deck of cards, then take off the top 2 cards, what's the probability of the first one being a heart and the second one being a heart? Well, here we have sort of a split probability. Okay, if the first event is a heart, the probability of B is going to be 12 out of 51 because we took out a heart. But the probability of B happening if A happened is going to be different. It's going to be 13 out of 51. So there's two possibilities. Depending on what happened with A, if we got a heart out already or not, the probability of B is going to change. That's the idea of a lack of independence, right? The probability of B depends on what happened with event A. Lastly, we can take a look at problems that are not so obvious. For this one, it says we have some students in an AP statistics class, and some of them are male, some of them are female, some are left-handed, some are right-handed. We want to know if those events are independent. If a randomly chosen student being female and a randomly chosen student being right-handed, if those two events are independent. So for this type of problem, we have to take a closer look at the numbers, and we'll see here that we do have independence. And we'll take a look at an example. Right now, it's kind of like that. Okay. So here we're asking the same question. Is there a relationship between gender and handedness, whether you're left or right-handed? So we've got a random selection of a simple random sample of 100 Australian high school students, and they've told us their gender and their handedness. Okay, so the question says, does knowing that a random student is male affect the probability that they're left-handed? So we need to look at a couple things here. What's the probability that a student is going to be left-handed? That's the first thing we're going to ask. So if we look at our data here, we see that 10 out of 100, or 0.10 of students are left-handed, right? We look at all the students, 10 out of 100 are left-handed. All right, well, what's the probability of being left-handed if you're male? Oops, left-handed, given that you're male. So if we know the random student was chosen, we can see that they're male. What's the probability of they're being left-handed? Okay, so we're only going to look at the males for this question. We only care about those. So out of those 46, 7 of them were left-handed, which gives us a probability of about 0.15, somewhere around there. So it looks like there is a difference, right? The probability of any student being left-handed is about 10%. The probability of being left-handed, given that you're male, is about 15%. So we're wondering, those probabilities are not the same, and they're fairly different. So it does seem like there is some effect. If we know that a student's male, it affects our ability to predict if they're left-handed. Looks like they're a little more likely to be left-handed if they're male based on this data. Sweet, let's look at another example. So this one says we've got first trimester screening, which happens during the first trimester of a pregnancy and helps determine if there are any specific chromosomal abnormalities in the fetus. So according to a study published by the New England Journal of Medicine in 2005, about 5% of normal pregnancies are going to receive a false positive. So the test says that there are some abnormalities, but there actually weren't. Okay, so that's 5% of false positives. So our question here is, if we test 100 women and they all had normal pregnancies, what's the probability that there was at least one false positive? So the probability of at least one false positive. There's two ways to find this probability. The hard way and the easy way. The hard way would be to find out what's the probability of 1 out of 100 being a false positive. Add that to the probability of 2 out of 100, and then 3 and 4, and so on, all the way up to 100 false positives. A much easier way to solve this problem would be to look at the whole probability model, which would add up to 1, and subtract the probability of no false positives. So we've seen this rule before. The probability of at least 1 is equal to 1 minus the probability of none. Okay, so what's the probability that we have no false positives? Well, if the probability of a false positive is 0.05, then the probability of not false positive would be 0.95. Sorry for my handwriting there. That's not better. So we want to look at what's the probability of all 100 tests being not a false positive. So here we're making a big assumption. We're going to assume that each test is independent. So we don't know everything about what happened with this study. Were all 100 women evaluated by the same doctor, and maybe that doctor is more likely to give out a false positive. We're not really sure how the test works or any of those details. So we're just going to assume that whatever happens with the first woman's test doesn't affect the next woman. We don't know that for sure because we don't have all the information. But we're going to make that assumption, which means the probability of the first test was a false positive, 0.95, and then the next one was a false positive. We just multiply those together. And we want to do that for all 100 tests. So we're going to take 0.95 and multiply that times itself 100 times because we have 100 tests. All right, so now we just do a quick calculation here. 100 minus 0.95 to the 100th power. So we get 0.994. Okay, so there's about a 99.5% chance that at least one of these tests is going to come out with a false positive. And that makes sense. If we're testing 100 women and there's a 5% false positive rate, we'd expect about 5 of those 100 to be false positives. So at least one of them being false positive feels like a really high chance of that happening and almost a sure thing. All right, before we wrap up here, this idea of independence, we're going to take a look at the probability that all 100 tests are false positives. So we're going to solve this a similar way. The probability of one false positive is 0.05. And we want all 100 events to come out that way. So we're going to multiply that 0.05 times itself 100 times. And if we do that in our calculator, it's going to tell us that the probability is 0. And this is why I'm bringing this up, because the probability is not really 0. It's very close to 0. It's a super small number, and our calculator is just going to give up and say it's 0. So it's approximately 0, but if we actually put this into a different calculator, we might get a different result. So for example, if I throw this into Google, it'll tell me that the actual value is not 0, but it's really, really close, right? 7.8 times 10 to the negative 131 power. That's 130 zeros plus a 7. That's a tiny, tiny number. So it might as well be 0. It's impossible. right? It's not, well, it's not impossible. It's just incredibly, incredibly unlikely. So I wanted to bring this up because sometimes as we get into these calculations, we're going to see really, really low probabilities. And sometimes our calculator will tell us it's 0, but it's not really. It's just really, really unlikely.